Everybody, let's get started. All right, so welcome back. Happy Friday. So today we will be continuing the discussion we started on Wednesday about visualizations and go into a very specific kind of visualization. We'll do a little bit of a recap, and this specific visualization is called a histogram, so we'll cover that today and explain when we use that, why we use that. Cool. So a few announcements. Lab 3 is due today, and homework 3 should be out now, due next Thursday, turn in on Wednesday for bonus points, so kind of the usual there. And Lab 4 will be released on Monday, due next Friday. All right, so kind of the usual things. And then one other thing, I actually ended up finding a really nice article on the study I was mentioning on Wednesday's lecture, where they assess causality, so definitely check that out. I actually wanted to just show you guys, it was pretty cool. Some of the language they used here, it's very relevant to the way we've been introducing in this class. But I'll just read aloud kind of this part here. So basically it says, I'll just zoom in a bit so you can see this. So the larger trial, which is kind of the first direct poverty reduction evaluation in the history of the US to focus on early childhood, recruited 1,000 mothers with low incomes from postpartum wards in 12 hospitals in 4 US metropolitan areas. And basically, shortly after they gave birth, the mothers were randomized to receive either a large monthly cash gift of $333 a month or a nominal gift of $20 a month. So those were kind of like the two groups, almost like treatment and control. And again, the key here is they were randomly assigned. And so you're taking away any confounding factors that could be resulting in changes in the thing that they're trying to study, which is brain development of the newborn children. And so, you know, if you were to just observe a family on their own, and you were to observe some people who had maybe a higher income versus who had a slightly lower income, there's lots of other factors that could be causing them to have a higher income that could also cause, you know, a difference in the brain development. But in this case, you're taking that away because you're randomly assigning who gets the higher income, who gets lower income. And so basically further down in the study, they have this kind of interesting conclusion where they say, you know, because of the randomized control trial design, the authors were able to distinguish correlation from causation, concluding that giving money directly to mothers living in poverty can translate to changes in their infants' brain activity. All right, so this is definitely good to check out. They use a lot of the language that we use. This one's also pretty interesting. So they say, until now, we haven't been able to say whether poverty itself causes differences in child development or whether growing up in poverty is simply associated with other factors that cause those differences. So hopefully you guys can kind of be able to read at least this summary of the study and understand what they're saying. And it's a really nice example of exactly what we were talking about in this class. And they kind of carried out the data science in the correct way. So it's a great study. Cool. All right, so in terms of weekly goals, yeah, as I mentioned, we already went into kind of tables. How can we actually read in a table with a CSV file? We also did our first visualization, so we talked about how you can use a line plot, typically when you're trying to look at something sequentially over time. And then there's like scatter plots, which is better in a situation where you have 2 numerical attributes, but you might have multiple values for any given value on the x-axis. And then we also briefly mentioned bar charts, which is a way to visualize a categorical attribute against a numerical attribute. And so we'll kind of continue that today. We'll see that bar charts are actually really useful for a slightly different type of visualization. And this all comes to the idea of distributions. So what are distributions? So before we get into that, there's some terminology to kind of cover. So individuals, we're going to be using this terminology throughout the course. So individuals are basically kind of like the subjects of our study. They are the kind of entities whose attributes are recorded in the table. So every row is typically going to be an individual. So every row in your table is a different individual. And then for these individuals, we measure their variables or attributes. So every single column is a different attribute. Same thing as saying every single column is a different variable. So we observe these different variables for all of the individuals in our study. And so as we talked about last time, those variables or attributes can either be numerical or categorical, generally speaking. And we talked about how there's like some edge cases where you can have something that's like categorical but represented as a number. But essentially, that's the way to think about it, is either the values in a column are part of like some category, or they're just like a set of numbers that are ordered and have some meaning. And typically we have different values, otherwise it's not that interesting. And that's actually why it's called a variable, because the value varies across the different individuals, right? So if you have a column where kind of all the values are the same, it's probably not that interesting to study it. You typically want to study a variable where it's actually changing as you go from individual to individual. And the key thing there is each individual has exactly one value for these variables, right? So if you're looking at like age, like each person has exactly one age, and that's going to be represented in the table. Or for the movies, for example, I mean, I guess it's not technically true, but like you can kind of make an assumption that like each movie is just made by like one studio, right? If you wanted to support like multiple sort of options, you would almost make that like a new category. So if you had like a movie made by 2 studios, you would kind of combine them together and almost make that like a new category, a new studio, even though it's not really a new studio. So there's ways you can also represent kind of, more interesting combinations of things. But at the end of the day, they would just fit into one category of all the possible options, or one value out of all the possible options. And then what we're going to talk about today is each variable, each column has a distribution, right? So every column has a distribution. And what is a distribution? It's essentially just a list of all the unique values that that variable can take, and then the frequency of those values. So for example, if I'm looking at a table of a bunch of movies, then let's say I'm looking at like the studio column, what I could do is I could look at all the unique studios that there are. Like maybe there's hundreds of movies in my data set, but maybe there's only like 10 studios that are possible. And so what I would do is just look at the 10 studios, how often does each one show up in the entire column? So maybe like MGM shows up like 50 times, and like Fox shows up like 20 times. So you just basically count up how many times does each unique value appear in the column. That's the distribution. That's really all distribution is. And so distributions are useful because it gives you a sense of like what does the data look like kind of overall in aggregate. Like what % of these movies are coming from this studio versus another studio. So it lets you make those comparisons really easily. And it's kind of like a way of summarizing a column. So that's another way to think about it. Cool. So a few examples here. So this is a kind of survey question where they basically asked kind of adults how often they go online. And so you can see there's like, or how often they go on like daily versus like less than daily. And so that you can see that there's these different responses that are possible. And this is giving you a sense of like what proportion of the respondents are in each of these different categories. So this is actually a visualization of a categorical distribution. And so the possible categories are like almost constantly, several times a day, about once a day, several times a week, less often or never. And so you can see kind of the percentage of the respondents that fit into each of these categories. And then the other important thing is that if you add up the numbers inside these bars, they have to all add up to 100. So you kind of need to have 100% of like anything happening. And that's also going to be really important in a distribution. And so again, each individual gets mapped to only one category. So if you're a respondent, you only answer one of these categories. You can't kind of go into multiple or respond as multiple options. There are going to be questions sometimes where it's not like that. So this is not a distribution. In this case, the survey respondents are answering a question related to kind of a major reason they find it difficult to quarantine themselves for at least 14 days. And they're allowed to select more than one reason in this case. And so because they're allowed to select more than one reason, if you look at the numbers here, 40, 39, 23, 22, they add up to more than 100. So this is not a distribution. And again, it's for like a couple reasons, but the main one is that each respondent is allowed to pick more than one answer. And so in that sense, you can't really look at it as a distribution anymore. And so if the numbers aren't adding up to 100%, it's not a distribution. So those are the main kind of differences here to just keep in mind as we're talking about distributions. Any questions about that? Cool. All right. So there's actually going to be 2 kinds of distributions that we're going to talk about today. One is distributions of categorical attributes. One's going to be distributions of numerical attributes. So we'll start with categorical attributes because they're a little bit more straightforward. Numerical have a little bit of care that we have to take, a little bit extra care. But let's just take a look at categorical to start with. So we're going to actually just take a look at that same table that we had in the last lecture, towards the end of the lecture, basically top movies as of 2017. So we're just doing table.read table, again, just reading in this CSV file, and then we can just take a look at it again. So here we have 200 movies, and we have the title of the movie, what studio it came from, what was kind of the gross earnings adjusted for inflation, and then the year that the movie came out. And so, as I've been kind of alluding to, we're just going to focus on the studio column. All right, so the studio column, as we can see here, we have different values like MGM, Fox, Universal, Paramount, and so this is a categorical attribute. You know, the responses in this column are just kind of categories. They can't necessarily be compared in any way numerically. And so what we're going to do is we're just going to take a look at the studios column. So we're going to do top movies.select studio. We're just going to assign this to studios. And so we just have, this is actually a table, but it's a table with one column. And so this column just has studio in it, and it has all the values. So we've kind of removed everything else from the table. And then if we want to actually look at the distribution of this column, so we want to actually look at the distribution of the studios in this data set, we can use a new function called group. And so we haven't introduced this before. We're going to go into more detail about this function next week, I think on Wednesday. But group will let you basically calculate the distribution of a column with just one line of code. So as you can see here, it's doing kind of essentially what I was saying, which is it's listing out all of the unique values of studio. So notice how we're not seeing any repeats anymore. And then on the right, we have how often do they appear. So, you know, Columbia appears 9 times, Disney appears 11 times, and so on. So we can very quickly get a sense right away in this entire data set of movies, how often does each studio appear. And this is our first look at a distribution. So any questions about that? Yeah. Yeah, that's a really good question. Does it automatically create a new column called count? Yes, it does. So when you use group, so you call it by just calling .group on your table, pass in what column name you want to group on, and then the group method will automatically create this new count column for you. And so that's good to keep in mind if you're ever using group. Like, you should expect to see that count column there. Yeah. Yeah, so what happens if you use group on the entire table instead of just a specific column? So you do need to specify a specific column that you want to group on, and there's like additional parameters that we'll go into next week. Now, I could have called .group on the original table instead of the studios table, and again, we'll go over that next week. But the result's actually pretty similar though. Any other questions? All right, so this is one way to look at a distribution of a categorical attribute. You know, it's basically like in a table format. It would be nice also, though, to be able to visualize this in a visualization, like a chart. So any ideas on what chart we could use to visualize what we're seeing here? Any thoughts? Yeah, the bar H, right, the horizontal bar chart. Because basically what we have here is we have one column that is categorical, and then we have one column that's numerical. So it seems like out of the ones we've at least learned so far, the bar chart is kind of the only one that will actually work for this one. The other ones are all assuming you have 2 numerical attributes. So let's take a look at how bar charts are useful here. So in this case, what's going to happen is we're going to make a bar chart of that table that we just created. And what the bar chart's going to show us is it's going to have one bar for each category. So that's a really important distinction from how we introduced bar charts on Wednesday. Because when we did the bar chart on Wednesday, we just kind of ran it on the table, and we saw that you could have had the studio show up multiple times. In this case, the studio will only show up once because we've grouped it first. So we've grouped it first. Now we're going to make a bar chart, and so therefore there's only going to be one bar for each category. We're going to be able to customize the order of the bars. We'll show you that in a second. And then the really important thing is that when you're looking at this bar chart, the length of the bar corresponds to the percentage of individuals that are in that category out of the entire data set. And so if you see a longer bar, there's a higher percentage of individuals in that category as compared to like another category, right? And so we'll just actually do this in Python as well. And it's actually pretty simple. It's just one line. So we can take this studio distribution, which again is the table that we just created up above, and then we just call bar H on it, passed in the studio column. I mean, it's the only column, but you still have to specify it. And so we get something like this. So I can zoom out a little bit so you can see it a little bit better potentially. And so what it's doing here is it's listing out every single unique value, again, because we already did that in the table. And then it's just showing us kind of relatively how often does it appear. So again, Buena Vista appears a lot more often than Columbia. It looks like maybe roughly, I don't know, what is that, like 3.5 times as often or something. And so you can kind of use this to really quickly compare any two categories and get a sense of how often they appear. One thing with this is that it's a little bit difficult to really interpret what's going on here, because if I wanted to compare two things, it's not totally clear every single time. Like if I'm comparing Buena Vista to Fox, it's really obvious that Buena Vista is more. But for example, if I'm comparing like, I don't know, Paramount to Sony, like I can't really tell. Like one of them could be longer than the other, but it's a little bit hard to eyeball it. So instead of ordering it alphabetically, which is what's happening by default, it might be helpful to actually order it by the actual values, like the length of the bar. Maybe that'll make it really easy for me to just see which one's more than another. And I can compare any two categories really easily. And so we can do that using the sort method. So we can just take our table that we have, which is studio distribution, and then we can sort it by the count. That's the column that we should expect to see on there. And we're going to sort by, let's just do descending equals true, because I want taller bars at the top. And then we just do bar H again. So it's kind of the same mechanism that we just did above, except we just did a sort before calling bar H. That's just one extra step there. And then if we can run this, now we see the exact same set of data, but it's ordered in a way that's a little bit easier to interpret. And so I can actually go back to that question I had, which was which one was more, Paramount or Sony, and I can confirm that Paramount, is at least as much as Sony. They could be the same, but it's certainly not less than Sony. I know that at least here. Yeah. Yeah, so does the length of the bar correspond to the percent or the count? So technically it corresponds to the count, as you can see at the bottom here. But the way it's also made is that you can interpret it as like the percent as well, like relative heights, right? So think of it like that. And so yeah, so this one up here, Buena Vista appears 35 times, and then we have Warner Brothers appearing slightly less. So these are actually counts, I believe, because this is already adding up to more than 100 just for these first 5 here, right? These are all like more than 20, almost more than 25. So it's actually the raw counts, but you can kind of interpret the relative values really easily here. That's what's important to keep in mind too. Yeah, good question. So one question for you guys is, why do you think the bars are equally wide? Or I guess I should say equally tall. Sorry, not equally wide. Like, each bar, it's kind of the equal height on each one. Why do you think that is? Like, we didn't really need to do that. Any thoughts? Yeah. Yeah, so the areas are proportional to the count, right? So when you're looking at a visualization, you want it to be really intuitive. And so if this Warner Brothers bar, for example, was like twice as tall as all the others, and it was still the same length it is right now, it might be kind of confusing, because you might think like, does that mean there's a lot more Warner Brothers movies than Buena Vista, even though it's not as long, but it's a lot wider, so that seems like it conveys more. And so it's just, you want to be consistent. And so in general with visualizations, area is kind of like the source of all truth. So when you're looking at the area of something in a visualization, that's really telling you how big something is relative to something else. And so if you want to keep the areas comparable here, it's just a lot nicer and consistent to just make them the same height every single time. And this is going to become really important when we look at numerical distributions. Because when we go to numerical data, there isn't a clear way to make categories with numerical data. You don't have like separate categories of numbers. That's not a thing. And so with numbers, you're going to have all kinds of weird shapes. And so it's really important to be able to compare areas. And so with categories, it's nice. They're all the same. You can just do the same height on each one. Cool. All right, so that's bar charts. Again, bar charts to use for visualizing the distribution of a categorical attribute. And then we have numerical attributes. So for numerical attributes, as I just mentioned, typically your numerical values can be like anything. Like it could be like 3.5, 3.7, 3.875. Like there's all kinds of combinations of numbers you could have. So you can't quite just put them in like categories and like draw a graph in the same way. Like I can't really like list out all the unique values and then count up how often they appear. I mean, if you have a, I guess, interesting enough data set, every single numerical value might only appear once, right? If you're measuring like someone's height all the way up to like the 6th decimal place or something, and you only have like 100 people in your study, like they're probably all gonna have a different value of height. And so your distribution's not gonna look very interesting because like everybody has a different value. So it's just gonna be like all their values in like 1, 1, 1, 1, 1 all the way down. So that doesn't really make sense. So typically if you wanna analyze numerical data, you need to do something a little bit more creative, and this is called binning. So you bin your values together into groups, and you essentially like make them like a category almost. And then that allows you to then have like some actual interesting numbers in each bin, and then you'll see that you might have different values across bins. So I'd like you to do this in an exercise as well. But basically what we're gonna do is when you're trying to create a visualization of numerical data, the first thing you're gonna wanna do is come up with a range of values. So you're gonna come up with like different ranges, which are gonna be kind of like how I bin these values together. And then we're gonna define these bins by their lower bound. So that means kind of like the lower value. So every bin is gonna have like a number on the left, a number on the right. And so the lower number is gonna be how we define it. Oops, sorry. And then the upper bound is gonna be the lower bound of the next bin. So the upper bound doesn't include the actual value. So we'll show an example here. So let's say that this is what your data set looks like. So this is some column of values, and I have the numbers like 188, 170, and so on. And then so let's say I'm trying to make a visualization of the distribution of these values. And so what I'm gonna do for my choice of bins, and again, this is maybe arbitrary, but I feel like I like having bins that are 5 apart every single time. So I'm gonna make my bins 160 to 165, 165 to 70, and so on, all the way up to 190. And then what we're gonna do is we're just gonna take each of these values and assign it to a corresponding bin, depending on which one it fits into. So for example, the number 188, that would go into the 185 to 190 bin, because it's between 185 and 190. So we would kind of start drawing it like this. And so this is called the 180, 190, 185, 190 bin. And it's really important actually to notice the characters we're using here. We have a bracket on the left, but we have a parentheses on the right. So what this means typically in mathematical notation is that this range includes 185, but it does not include 190. So it's like every single number up to, but not including 190. Right? So that's really important to keep in mind. And that's how we're going to define all of our bins. So they're always going to be this way that like it includes the left side, but it doesn't quite include the right side. And so 170, the next number, that would be drawn in the 170 to 175 bin, because this bin contains 175, whereas the bin on the left does not contain 170. It's up to, but not including 170. So we draw it like that. So maybe you guys can help me out for the rest of these. So you can just say this out loud, but the 189, which bin does that go in? Yeah, 185 to 190, right? So we can add that there. Whoa, that's weird. Are you guys seeing that too? Okay. So that adds to that one. And then 163, where does that one go in? Yeah, 160 to 165. How about 183, where does that go? 180 to 185. How about 171? 170, 175. How about 185? Yeah, so this is a 185 to 190, right? So a little tricky, but again, remember this range here, 180 to 185, doesn't include the number on the right. So always for bins, it does not include the number on the right. It's everything up to, but not including. Right, so you guys get the hang of it. So basically, as you can see now, as we fill this up, it's starting to look a little bit like the bar chart did, even though this is numerical data. So we've almost like converted this into a form where we almost have like categories, and so we can sort of count up how often a numerical value is in each category. And so now we have a nice way to actually visualize the distribution. And so as you saw, we just chose the range ourselves. You could have chosen different ranges. Maybe if you wanted, you could have done a ranges of 10 instead of 5, right? And so that's something to keep in mind too, is like the distribution that you're actually creating, there's a little bit of subjectivity behind that. And the data might look slightly different depending on what you choose for your ranges. But it's just important to be consistent and just be aware of how the ranges were chosen and what you're actually seeing. Cool, so let's actually go take a look at this with some data here. So in this case, what we're gonna do is same data set, but we're gonna look at the ages of these movies. So we have the year that they were made. We're gonna make a new column called age. We actually did this at the end of last lecture as well. So we're just going to take top movies column year and subtract that from 2022 to get the age. And then we're going to add that into top movies as a new column called age. So that's all we're doing there. And I guess we can just take a look at this as well, just to make sure. So all we've done here is added this column at the end here called age. So 1939 becomes an age of 83, and so on. And then it's also helpful, we want to make a visualization of the distribution of the ages. So we're going to have to make some bins for these. It's always good to get a sense of like what is the entire range of your data. So you can do that really quickly in Python by just checking the min and the max. So I could just do min ages, max ages, just as like a gut check. So you can see the minimum age is going to be 5, the maximum age is going to be 101. And so with that in mind, then you can make some bins. So for example, let's just call these my bins, make array. And so I'm just going to put some numbers here, 0, 5, 10, 15, 25, 40, 65, 100. Actually, let's do 105, so we include that 101. And so I just made up some numbers there. And then if I wanted to actually put these data together in a bin, there's a bin function that lets us do that. So we can do bin data equals topmovies.bin, and then we choose what column we want to bin on, and then we pass in the actual set of bins that we've created there in our array. And then we can take a look at what this shows us. And so here you can see that this looks a little bit similar to what the group method was doing in the categories case. It's essentially kind of converted our numerical data into categories almost. And so what it's saying is basically the 0 to 5 bin has 0 values in it, and then the 5 to 10 bin has 25 values in it, and so on. And then at the very end, you have 65 to 105 that has 21 movies in it, and then there's nothing at the end beyond 105, so it just puts a 0 there. But the 0 really just means like that's the last bin, so it's never going to actually show any number there. But it's just a way to signify like the end of your bins. And so hopefully you can see this looks kind of similar to the categorical case, but we're just kind of doing this with numerical data now. And so we chose these values kind of arbitrarily. If we wanted, we could do something slightly different. So we could do like equally spaced bins instead of just these like arbitrary values that I did above. And so to do that, you could use np.arange. So that's a really nice way to do it. So we could do np.arange, let's say like 0 to, like 125 in increments of 25. And so I could do it that way as well. Actually, let's do 126, sorry. There we go. And so then it'll make, np.arange will basically do like 0, 25, 50, all the way up to, but not including 126. And so we get 0 to 25 has 81 movies, 25 to 50 has 70 movies, and so on. So we can see all the different values there. So any questions about that? Should every bin be the same size? It doesn't have to be necessarily. I think it's probably more intuitive if you do it that way, but it's a good habit to start getting used to looking at distributions that do not have that. And again, the reason for that is because as you look at additional data, and also later in the class even, we're going to see cases where instead of bins, you're actually going to have like almost like a continuous set of values and like a smoother like curve instead of just bars. And so in order to interpret a visualization that has like a smooth curve rather than just a bunch of bars, it's important to be able to compare areas of different widths. And so that's why it's good to just get in the habit of seeing distributions with different size bins. But in general, if you're making your own, probably equally sized bins is usually like the way to go. It's pretty intuitive. How do we get the age count? Is that automatically generated when you call bin? Yeah, it is. So the bin method works really similar to the group method that we used previously for the categorical attributes. So it does count the ages for you. It doesn't use just count, unfortunately. This method does like a slightly different thing. It takes the original column name and just adds count to it. So not sure exactly why that was done, but anyways, it's slightly different. And it also creates this bin column, which is also a little bit different. But yeah. Cool. All right, so now we know how to kind of at least make bins out of our numerical variables, and then that then sets us up to be able to visualize them. But before we visualize them, it's good to just go over one other thing, which we actually alluded to earlier, which is this concept of areas, the area principle. So this is a really good example of misusing the area principle, potentially. So this is from several years ago, and they were kind of trying to compare the battery life of like a new iPad versus like the previous iPad at that time. And then the caption for this graphic said the new iPad battery is 70% bigger than the previous iPad. So any issues that you guys see with this visualization? Yeah. Sorry, they're talking about the battery size, not the battery life, yeah. So like literally the battery size, so assume it's battery size. So just take a minute or so to just look at this and see if you see any issues with this visualization. What's that? There's no scale. Yeah, so that's definitely an issue. It would be nice to have some sort of scale on this visualization, right? But even without the scale, like the caption at the bottom where it says 70% bigger, like does that larger battery look 70% bigger to you guys? Does it seem more than 70% or less than 70% bigger? Like you want the relative value. Like ideally, I should be able to figure out what's going on here even without a scale. That is a really good point, though. There isn't a scale, and that's not good. But even without a scale, I should be able to see like what's going on. Yeah. Yeah, so it looks almost 4 times as big, right? So if it's 70% bigger, that's like almost twice as big, essentially. Like if it's 70% bigger, it's like 170% the size, so it's like almost twice as big. So I would expect this battery on the right to be like around twice as big, maybe a little bit less than twice as big. But it actually looks like 4 times as big, because if you look at it, it looks like twice as wide, and it's also twice as tall. So the area is actually 4 times as much. I could fit 4 of these batteries almost in the battery on the right, which doesn't make sense. So this is kind of making it really dramatic, the change that's there, and it's not really being an accurate representation. And so this goes back to the idea of area being the source of all truth. You want area to represent how big something is relative to something else. If a visualization is not doing that, then it's not accurate. And so a good way to simplify this is if you're representing 20% of a population with a little triangle like this, then 40%, which is twice as much, should be 2 triangles effectively. It shouldn't be a really large triangle that's like twice as wide and twice as tall, because you could actually fit 4 triangles into this really big triangle. So you have to be really careful there. And maybe this is just like an honest like math mistake, but just, you know, that's a good gut check as well, right? Like when you're making your visualization. Like if I know that this like one category or this one bin is like twice as much as the other one, I should expect that the area that I'm seeing for that category or bin is twice as much as this one. If it's more than that, then something's maybe going wrong, right? So that's the main thing to keep in mind. And this is going to be how you're going to interpret histograms and in general, like visualizations for distributions. Cool. All right, so how do we actually draw a histogram? So what is a histogram? So histogram is just another way of calling the numerical distribution. So that's the way that we actually visualize the numerical distribution. So when we visualize a categorical distribution, it's called a bar chart. When we visualize a numerical distribution, it's called a histogram. And so how do we actually do this? And what is it exactly? So it's going to display the distribution, and it's going to have one bar corresponding to each bin. So we're going to, just like the bins that we made before, you're going to have those bins along the bottom, and there's going to be one bar shooting out of each bin. And again, remember that the bins that I chose in that original example, they had slightly different widths. Some bins were wider than others. So you should expect to see for numerical data that some bins are going to be wider than others, whereas with categorical, you wouldn't expect that. But that's okay, because you can use the area principle. And that's basically going to say that the area of each bar is the percent of individuals corresponding in the bin. All right? And this is going to be important later in the course, because we're going to start, instead of using bars, we're going to use smooth curves like this. And so if you want to compare 2 different areas underneath the curve, you're going to need to be able to do that without making assumptions about equal bins and things like that. And so that's kind of the main reason why we try to teach you that now. But you don't have to worry about this right now today. Oops, sorry. Cool. So let's actually do an actual visualization here. So we're just going to show these bins again. So these are these arbitrary bins that I chose. So the first bin was like a width of 5, but then over here it got to like a width of 15 and then a width of 25. So it started to kind of like stretch out almost. And then we also put this into an actual table. So we had the bin data table, which contained all the bins above and then the counts within each bin. And so what we're going to do is try to make a visualization of this. But before we make the visualization, it would actually be helpful to get a sense of like what percent of the data is in each bin. Because we can see the counts here, but it's actually a good idea to just compute the percent. And so the way we can do that is we can just take this bin data column, which is age count, and then we can divide this by 200 because there's 200 movies in total. And then just multiply by 100 so we get a non-fractional number. And so all we've done here is just taken these values in this column, divided by 200, and multiplied by 100. And so what this is saying is 0% of the movies are in the 0 to 5 bin, 12.5% of the movies are in the 5 to 10 bin, 8% are in the 10 to 15, and so on. So we've just converted the counts to percentages here. And this is just going to be helpful as a kind of like a gut check when we're looking at the actual histogram to just make sure like the percentages are kind of corresponding to what we would expect. And so let's actually make a histogram. So what we'll do is, we'll take our top movies table, and then we call the hist function. So instead of bar h, we're doing hist here. We're going to specify what column do we want the histogram of. So we're going to pass an h, that's the numerical column that we're interested in. How do we want to bin this? We're just going to use the bins that we came up with. And then what are the units for the bottom axis? Age is in years. So we have to specify the units. We're going to do that here too. And so it creates this visualization here. And so these are the different bins that we created along the bottom. So we had 0 to 5, 5 to 10, I believe. 5 to 10, 10 to 15, and then 15 to 25, and so on. And then you can see what's in each one. And so the area in this case is corresponding to the percent of the data that's in that bin. So this first bin, 0 to 5, has 0% of the data, so there's nothing there. The second bin has 12.5% of the data, so that's what we're seeing here. So this entire bar should be 12.5% as we saw. Then if you go to the next bin, it should be a little bit lower, so 8%, and so on. This one's 20%, but notice how it's shorter, but it is wider. So the area principle is what's going to be helpful here, right? So the second bin is much wider. It's like almost twice as wide as this really tall bin over here. And so that's why it ends up having a higher percentage of data, even though the height is actually lower. So any questions about this visualization? Yeah. Oh yeah, why did we divide by 200? That was just because the total number of movies was 200. So if you sum up all the values in this column here, the age count, it's 200. So we wanted to take the number of movies that are in each bin divided by the total number of movies so we can convert to a percentage. Yeah. Yeah, is a vertical label automatically determined? Yes, it is. So this percent per year, it's automatically determined for us based on what we put as units for the horizontal axis. So if your horizontal axis is years, the vertical one's always going to be percent per year. And the reason for this is because we talked about how area represents percent, right? So if I'm looking at the area of a rectangle here, the units of that area is percent. And then the width of the rectangle is years, because that's the units on the bottom. And I know that width times height, or width times length, whatever you want to say, needs to equal the area, right? So basically like years times something needs to equal percent. So that something needs to be percent per year. So just move the year down. That's actually how it comes out. So in general for histograms, that's how it's always going to be. It's going to be, the height is like percent per whatever unit you have in the numerical data set. Yeah, so that's a really good question. Cool. Any other questions about this? Cool. All right. So, oh, you know what? It's worth actually just taking a look at what this looks like if we use equally spaced bins, just so you can kind of get a comparison here. So let's do np.arange 0 to, was it 126, let's say, 25. Actually, let's do 10, so it's a little bit closer to what we did here. Let's do 111. There we go. So let me zoom out so you can kind of compare them. So this is kind of the effect of having equally spaced bins versus having just your own like customized set of bins. And so overall, it looks pretty similar, right? But this one has like a little bit more detail, maybe a little bit more nuance there that like you don't really have a lot of movies after 100. Whereas in the top visualization, it seems like, I don't really know, like there could be equally as many movies after 100 as, you know, below 80. But you can see here that's definitely not the case. So, you know, it's just a slightly different way of looking at the data. They're both valid approaches. You know, it just depends on what you're trying to convey. Like if you're not really that interested in movies that are like more than 8 years old, then the one on top maybe is okay. But if you're actually trying to understand something about those older movies specifically and like the differences between them, then the bottom one might be better. So it's really kind of up to you and what type of story you're trying to tell, what are you actually trying to understand about this data set as well. And then there's also, if you don't specify any bins, you can also do that too, actually. So you could actually just do this without even specifying the bin. So I can just take this whole thing and delete it. And so it's just hist age with unit. I can also do this. But one issue with this is I really have no idea what these bins are. Like Python just chooses some bins for me automatically. But I don't quite know, like this bin, like what is that? Is that like 17, 15? Like I have no idea. I can't really tell. And where does it go to? It just picks like kind of weird values sometimes. That's you don't really know what you're seeing. So basically, choose your bins. It's kind of up to you how you want to choose them. But you know, just be reasonable. Don't necessarily do like bins of one because that may not be very interesting. But you know, big enough, but maybe not too big. Cool. All right. So I guess we have a few more minutes. So the last thing to talk about is height, this concept of percent per unit. What does that mean? So some good questions came up about that, so let's actually go into this. So this percent per unit is actually called density. There's actually a name for it. And so just to kind of recap what the different axes are, or I guess the general histogram in general, right? So first of all, this histogram is created so that the sum of all the area is going to be 100%. Again, very similar to what we were talking about at the very beginning. If you're looking at responses to some question, if the distribution doesn't sum up to 100%, it's not actually a distribution, basically. So you know, it's important that everything sums to 100%. The area is a percentage, and the horizontal axis is whatever units you have for your numerical value. In this case, it was years. And then the height, as we said, the vertical axis is percent per year because it's area divided by width. That should be the units of the height. And so a lot of times you can think of it like a rate, like percent per year, miles per hour, it's just like a rate. But really it's giving you a sense of sort of like crowdedness and like how much stuff is in that particular area versus like another area for every like incremental year. So if you go back to the visualization here, if you just go back to this one, for example, what this is basically saying is like for the 25 to 40 age period, there's a lot more movies per year than there are from the 40 to 65 period. So that's one way to interpret it, is like rate. So you know, this is almost like a higher percent per year, a higher number of movies per year during this period versus another period. So that's one way to interpret it. And so basically what this is saying over on this visualization is like, if you look at all the top movies as of like 2017, at least historically, if you go back in like kind of the timeline, there's fewer movies being made per year in like the really, you know, past like 65 years ago that ended up becoming like in the top movies today as opposed to like more recently. So you can kind of see that difference. And so it's just kind of a sense of rate or how often things are happening. And if you wanted to actually calculate the height of a bin, we could do this too. So let's actually just take, for example, the 40 to 65 bin. So let's say we wanted to calculate the height of the 40 to 65 bin. There's basically 3 steps to doing that. So the first is determine the area of the 40 to 65 bin. So that's just the percent of data that's in there. So we can actually just write this out here. So this percent would just be bin data dot where. The bin is 40 because again, the bin is defined by its left value. So we just look up the row corresponding to 40, and then we just take the percent column from that. And then we'll just take the first item in that column. Oh no. Percent is not in the table. Oh no, really? Let's see, what's in the table? Oh, I forgot to add it to the table. So let's actually add this to the table here. Sorry about that, guys. So let's do this as percents, and then we're just gonna add this to the table with the column, percent, and then just put in percents here. All right, so this should go through, and then we can just take a look at what percent is. All right, so you get this kind of weird number, but basically 28% is what is in the 40 to 65 column. So we have the percentage that's there, then we have to calculate the width of that bin. So the width of this bin is pretty easy to calculate, but let's just put it down anyway. So width is just gonna be 65 minus 40. That's it, that's the width. So we can just check there, so 25. And then lastly, because the area is equal to the width times the height, in order to calculate the height, all we do is take the area, divide out the width. And so in this case, the height is just gonna be percent divided by width, and then we can take a look at what the height is. And so we get 1.12. And so this is 1.12% per year. That's the height of the 40 to 65 bin in the histogram. And so you could do the same process to calculate the heights of any of the other bins. And then we can actually go and just double check on the visualization as well that that's kind of what we're seeing. So 40 to 65 is right here. And so this is 1.12 is what apparently is the height of this. And so if you look at this, it's like somewhere between 1 and 1.5, but like pretty close to 1. So that seems reasonable. Seems like it's not a totally ridiculous value, and we didn't mess up anywhere. Yeah. Yeah. So you're saying sometimes the bins can be shifted, and then it's harder to interpret? Yeah, I mean, the best way to make it kind of more uniform is just to do equally spaced bins. That's usually the way to do it to make it more comparable. Yeah, I mean, those are usually going to be kind of the two ways you'll see most histograms. Either it's going to be something like this, or it's going to be having the equally spaced bins. In reality, like the reason this is actually going to be useful later on is if you, in the slides we showed that curve, right? So what's going to happen is we're going to start approximating these bars with like a curve. And so then you might see a curve go down like that. And so that's the main reason why it's important to be able to understand a histogram when it has like different widths. But in practice, you shouldn't really be seeing too many things like this, actually. Usually people will just use equally spaced bins. Cool. Yeah, and so just as a recap on how to calculate the height, so you know, basically you take a look at your bin, understand how many things are in that bin. In this case, it was 56 out of 200 movies. That corresponds to 28%. That's the actual area of the bin. That's the entire area of the actual rectangle. And then we also know it's 25 years wide. And so if you want the height of the bar, we just take the area and divide it by the width, and that gives us the height. And it also explains why the units are percent per year, because it's literally 28% divided by 25 years. Cool. And so basically the height is kind of measuring the percent of data relative to like a small amount. So that's kind of why we say it as like a rate. I think it's easier to think of it as just like crowdedness or density, maybe even like frequency is maybe like another way to think about it. And it's just always going to be percent per whatever units you have on the horizontal axis. So this was years specifically because that's what our data had, but it could be dollars or whatever units you have on your horizontal axis. Cool. Yeah, I think we'll stop there and then continue on Monday. Yep. Thank you.